Now we'll see data hazards. To understand data hazards, let's take two instructions and we try to execute in a pipeline fashion so that you will understand what is data hazard. We are going to stop the pipeline and we need to stop the pipeline because of this data hazards. There is a dependency. We'll see. Slowly we'll understand. First of all, blindly, understand how this instruction will be executed and what are the various phases. So in the first step, let's say call it as I1, then instruction fetch stage is going to fetch that instruction, right? Now I1 is fetched. Let me go a little bit quickly here because so many times we understood that in the first stage instruction will be fetched, right? Now that instruction will be kept in this buffer, right? So this is buffer 1, this is buffer 2, this is buffer 3, this is buffer 4, right? So in the buffer number 1 we have instruction 1. So in the second clock cycle what is going to have happen? So this decoder is going to generate control signals based on this input I1. Then appropriately at the same time these registers also will be read, correct? So what are the registers we have to read here? We have to read R1, R2, R3. That means content of R2 will be read. Let us say content of R2, and that means in the decode stage we will be reading R2 and we will be reading R3. We will be reading address of R1, correct? So finally I can say that R2, R3 and address of R1 all will be forwarded to this stage. That means this buffer is going to have now R2, R3 address of R1. So example, let's say R2 content is 20, R3 content is 30. Then we will be forwarding value 20, value 30, which we will be reading in this decode stage from the register file. Did you remember? So in the register file we have R2, R3, we'll read them, we take the values, and apart from that, that register R1 address which is mentioned in the instruction, that will be forwarded. Okay. Now in the execution stage what happens, since this execution stage is connected to this buffer, so that R2, R3 will be added, 20, 30 will be added, that result 50, okay, which is nothing but R2 plus R3 will be forwarded to this buffer, and address of R1 also will be forwarded, so that this memory stage can make use of these things. But of course in the for add instruction memory stage doesn't require, correct? That means there is no work from memory stage. So that's why what this memory stage will do is it will simply move the content 50 to the next level and address of R1 to next level. In that way this buffer is going to have 50 and address of R1. Now if you see the timelines, so in the after first clock cycle this buffer gets instruction, after second clock cycle these buffers gets values, after third clock cycle these buffers gets values, after fourth clock cycle this buffer gets values 50 and address of R1, right? Now write back step. In the write back step, of course, this 50 will be stored in the address of R1. Okay, that will be done. Now we blindly execute this second instruction. Since in the first clock cycle instruction fetch stage is busy, we can't fetch that instruction, second instruction at the same time. We know that, that's why we will be using instruction fetch stage in the second clock cycle. In the second clock cycle instruction fetch stage is idle, we can use it. Now let me show instruction fetch here. Let us say decode here, here let's say execute, and here memory, right? Then here write back. Let us try to do the same thing for subtraction also. So we have buffer here, right? Let me show the buffer. Here buffer we have buffer, buffer. Let's say connections like this. So you might have doubts, sir, why you have written two cables here, two black lines. Of course, because the execution stage is nothing but ALU, right? So maybe in ALU you will be adding two inputs, that's why. So I use two lines like this, okay? Now, instruction fetch, in the first stage what happens, I2 will be fetched. I can say that at the second clock cycle, end of the second clock cycle, this buffer gets I2. At the end of the third clock cycle, so that instruction 2 will be decoded. Yes, at that time, so we can do decoding because only execution was busy. So in the decoding step, what we will be doing, we will be decoding and we will be understanding that R1 and R5, we will be taking the content of R1, content of R5, okay, and we will be taking address of R4, okay, which is written in the instruction. So address of R4 I take from here, okay. Now content of R1, content of R5 I take after decode stage. In the decode stage, I will be taking from the register file. So now slowly you understand here, if you execute, then R1 plus R5 should be added. But here the problem. Now if you see carefully, there is a mistake we are doing. What is that you see? In the first instruction, R1 is getting updated, right? When it will be updated? After write back step, right? So in the write back, at the end of this clock cycle, probably your register file on that R1 gets the right data at the 5th clock cycle, correct? So after the 5th clock cycle only you get R1's correct answer. But what you are doing is, you are reading R1 in the 2nd clock cycle, correct? We are reading here content. So if I read content R1, what is the content of R1 at this moment? 20. Sorry. So the content of R1 I did not show. Assume that, let's say, content of R1 is 0 for time being, okay? So but later, after executing this entire instruction, that is going to become 50. Then we have to take 50 for subtraction. But what is going to happen here is content of R1 0, which you are taking, right? So that will be absolutely wrong. So R1 gets correct answer only after this write back stage. Then what to do? We have to stop the pipeline. So here you can't do decoding. We have to stop. That's why what we do is, little bit we move this instruction. Somehow, let's say you know that there is a problem, otherwise there is a dependency between these two instructions. So we can do one thing. When are you going to get the result here, right? So I will fetch the instruction here. If I fetch the instruction here, is that fine? If you fetch the instruction in the decode stage, probably you will be reading, but at the same time, you know, that's why that is not good. So better you fetch the next instruction in this stage, right? Instruction fetch. So that when you do decoding, while doing the decoding, then the data is already available in the register, because already write back of the first instruction is done. So I want to say that here you thought of doing instruction fetch of the second instruction here, but where are you doing? Here. Then this one and this one, okay, so this one is wasted, this slot is wasted, this slot is wasted, and you are doing from here. Then how many slots got wasted? 3 slots will be wasted, right? So that's why what I want to tell you is, so data hazard is going to, you know, affect your performance of pipeline. Then sir, what to do? What are the solutions here? Solution number 1, easy solution. Somehow you detect that there is a dependency between the instructions in the software level, and you design your hardware such a way that whenever there is a dependency, appropriately your instruction should be stopped. That means, so your hardware should be stalled such a way that the next fetch should not be done. The next fetch should be done here. Such a way we have to design the circuit. That is one thing. Second one, we have another strategy, that is forwarding. One is stalling, second one forwarding. Data forwarding. So already I explained you what is stalling, right? You simply stall your pipeline until you get the answer, right data, right? Second one is forwarding. What is forwarding is, if you carefully observe, actually the data is already available somewhere, not in the registers, right? When data will be 100% available in the register? After write back stage. But where are you computing the data to be stored here? R1 is going to get 50, but 50 is coming from where? Here you see. So after execution stage, data is available, right? What we can do is, so here already this buffer contains 50, right? Somehow using your hardware connections, okay, we have to connect the things such a way that, so what should happen is, this buffer should be connected to, I will tell you. For that what I do is, I blindly, you know, execute the instruction like this. Let me do like this. Let us try here. Instruction fetch, and I don't stop. Decode. Okay. So let us continue. Instruction fetch, decode, execute, memory, write back. Okay. So we pretend like, you know, hardware will be designed such a way that instruction will be fetched, I2 will be fetched, and decoding will be done. Then wrong, you know, content of R1 comma R5 will be taken. Content of R1 comma R5 will be taken, which is wrong. Let me mark it. So R1 is wrong content. In the execute step, they will be given like this. But you see, so what we do is, we bypass like this. That 50 we connect like this. Okay, we use multiplexer. So the technical details are unnecessary. Unnecessarily they will complex the things. But we use multiplexer. That multiplexer will decide, sometimes this cable, sometimes the original cable. Now see, this execution stage is going to take either data from the decode stage, otherwise data from the, this buffer. Okay. That means what? Finally, decode execution in between. Okay. So there is a buffer, right? We have to send this 50 to this buffer. What is that buffer? Decode execution buffer. There is a buffer, right? Decode execution buffer. What is this buffer? Execution memory buffer. The data in the execution memory buffer should be forwarded to data in the decode execution buffer. Though I am showing in the next line, but this is equivalent to this, entire circuit is equivalent to this circuit. For convenient, we are writing in the next line, but this decode and execution buffer is nothing but this decode and execution buffer. Finally, we have to forward from here to here. That means in the connection wise, we have to forward like this. So that what happens, see, better, I show in the parallel lines. So what is going to happen, we will see. Whenever there is a hazard like this, so R1 is connected like this. Assume that, let's say, this 50 also connected. But the multiplexer will smartly decide whether 50 to be the right input or this one. In this case, definitely 50, right? So in that way, this is called forwarding. Understand? Generally, rather than going into much technical details, simply we say like this. So the data which is already available after the execution stage, we connect like this. Okay. So now this will be bypassed. That means, we don't consider this one. It also comes because that decode, unfortunately, this decode stage doesn't know, right? So that's why we simply take the data, original data, but we don't use it. Because of one more connection, what happens? This path will be chosen appropriately because of the hardware. So hardware will be connected like this. There will be a multiplexer. Assume that this is through original line. Okay, original line. Second cable is this forwarded cable. So that, but only one thing should be taken. There will be a control line. What we do is, whenever you are implementing pipeline, so this select line will decide everything, this control line. Example, there is no dependency. Then we use original line. So appropriately this control signal will be generated. That means, example, 0 means this one, 1 means this one, then 0 will be generated. Now, if you want to take forwarded data like this, then this connection should be selected. For that, 1 will be enabled here, so that this will be selected. In that way, using this control signal, we can select one of them. Already we have studied multiplexers enough so that you can easily understand. So this is what happens finally. So because of forwarding, then you don't really require to wait. No waiting, right? So this is about data forwarding. Understand? Now already result is available here. Let me summarize. The result R1, which is available here, because R1 is actually going to be R2 plus R3. Somehow your circuit is designed such a way that knows that, second instruction is going to use R1. Then what we do is that result will be connected like this. Okay. For that how to design such circuits or intelligent circuit, we will see that. So it will be designed based on the instructions. We have to design a circuit based on the instruction possibilities, everything. That will be quite complex. For GATE exam, it is not really required. So we don't bother about that circuit, but we assume like this. Okay. So there will be a connection like this. So this is about data forwarding, right? Sometimes though you do data forwarding, no use. When, sir? Maybe at that time really data is not available. Here data is available but not stored in the result, right? That means, what is this case here? Data available. What do you want? R1, right? See, you want R1 for second instruction. That R1 is nothing but R2 plus R3 that is available. Sometimes what happens, data will not be really available. I will show one example of that. Okay. Now we'll see these two instructions. Load R1 100 of R2, add R3 R2 R1. Here you see there are two variables which are common in both instructions, right? R1 R1, second one R2 R2. But if you see carefully, we are not modifying R2, right? We are using R2. Here also we are using R2, we are not modifying. When both instructions are using R2, then there will not be any problem, right? So at any order they can be used. But the thing is, here load instruction is using R1, add instruction is using R1, but here R1 is getting updated because of load instruction. But this add wants to use R1. So what is going to happen, we'll see. Let us execute load instruction with these 5 stages. So instruction will be fetched here, right? You will be getting that instruction. Let us say I1 here. So I am not showing the buffers, but you can assume that there is a buffer here. There is a buffer in that way, 4 buffers. Now in the decode stage, what is going to happen? We will be reading all the identities, right? Like, probably we will be reading here R2, correct, content of R2 and address of R1, right? We will be reading R2 comma address of R1, remember it. Okay, so let us use value of R2, address of R1, remember them. Okay, so we are using, there is a difference, we are using value inside the R2 and we are using address of R1 here. Okay, now third step, execute. In the execute step, 100 and R2 will be added, correct? So 100 also comes like this, 100 comes from the decode stage. So this 100 comes from instruction fetch stage, right? Finally 100 plus R2 will be added. So this execution step will give you 100 plus R2, that will be carried away, and R1 also. Here R1 means not content of R1, address of R1. Let us write address of R1 better, address of R1. Then after that, in the memory access stage, we will be accessing the memory. So using 100 plus R2, we will go to the memory and we'll fetch the data, right? So data at 100 plus R2 will come now, and that will be stored in the next stage, right? And one more thing, here address of R1 will be forwarded. Try to understand. So slowly address of R1 will be forwarded from the instruction here to here, here to here, here to here, and see, content is getting changed here. We used 100 plus, that, so I mean total stuff, right? So finally data at 100 plus R2, which is in memory, this is your memory. So at 100 plus R2 there is some data which has to be stored in address of R1, right? Into R1, of course. So we have already address of R1. So write back stage is going to do that. Now what I want to tell you is, finally the register R1 is getting updated here. That is what I want to say. Finally here you will be having the original data in R1, right? Before that everything is wrong. But here add instruction wants to use R1. Where it is using that R1? So slowly, forget about that, data forwarding everything. First of all, really, if this instruction is executed independently, then what is going to happen? So we will be fetching the instruction here I2. Then decode stage will, send content of R1, content of R2. Now we have content of R1, content of R2 and address of R3, correct? Now we have content of R1, which is wrong, which is going to be feeded here. So execute step is adding R1 and R2, right? But R1's content is wrong. But if you see the timeline, at time 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock. So after 5 o'clock, R1's data is available. But you want that at earliest at 2 o'clock, right? 1 o'clock, 2 o'clock. At the end of the 2 o'clock, you want R1. But at the end of the 5 o'clock, R1 is available. Then how can you forward it? Sir, I will forward like this. How? Like this. The result, which is going to be, so here you are going to get, before that itself we have answers at 100 plus R2. So data at 100 plus R2, which is available here actually, correct? Sir, I forward like this. Yes, you can forward like this, but you are trying to forward like this. Sir, I connect this R1's cable, that means whatever the data connection. So I forward like this. Where is the execution stage? Here, right? I connect like this, sir. If you do that, then probably what are you getting? So you are connecting this data at 100 plus R2, which you got through memory access. You are connecting like this, perfectly right. But you see this connection, when are you forwarding? After end of the 4th clock cycle. You want to forward it after end of the 4th clock cycle to the position where it's at the end of the 2nd clock cycle. That means you are traveling through time backside, right? Is it possible? How can you forward the data to backside? It is not possible because this data you are forwarding at the after fourth clock cycle to second clock cycle. We can't do that, right? We can forward data from fourth hour to fifth hour to sixth hour, fifth to 10th. But how can you forward the data from fifth hour to second hour? Second hour is already done, correct? So that's why this kind of backward forwarding is not possible. So forwarding backside means what? You are going back in the time. That's not possible, right? So that is quite easy to understand. Then what to do? Here definitely we have to stall it, correct? So that's why here stalling is required. We can't, there is no alternative. Sir, we do something and we do forwarding, sir. To do forwarding, see, at the earliest you have to forward like this. That means at least you should have data available here. But I don't have data available here because after memory access only I get the data, right? That means we have to access the memory in the execute stage. Are we doing that? No, we are doing definitely at memory stage. So that's why the earliest time data will be available is at fourth clock cycle, after fourth clock cycle. But at the earliest you require data is at second clock cycle, end of the second clock cycle. So that's why there is a problem. We have to avoid that. Then what to do? We'll try to do some alternative strategies. For this one definitely we have to stop, and we have other solution. So far what are the things you have seen? One is stalling, right? Stall the pipeline. Second one, data hazard solutions are stalling the pipeline. Second one, forwarding, but here forwarding is not possible. Then what to do, sir? The third strategy may be reordering the instructions. Sometimes by reordering the instructions we can get some time, we can have some time. Example, let's say in between these two, if there is another instruction, somehow if your compiler places it, okay, so your compiler knows that there is a danger of pipeline stall, and if it somehow inserts one more instruction, so that you will be fetching this instruction little bit further, right? That means maybe here, when rather than fetching at second clock cycle, if you can fetch this one at third clock cycle, you might have advantage. Probably by that time data might be available, right? So that is nothing but for reordering the instructions. I will explain the reordering instructions with one problem. Okay, there is a small correction actually. So here actually the time is 2, right? Not 1. Okay, second clock cycle. This is third clock cycle. So with that, now so finally what is the thing is, so the earliest time the data will be available is after fourth clock cycle. This is correct. But the earliest time data you require is after third clock cycle, because you want to execute addition. For that R1 is required. So here you need an input, right? So that means at the end of the third clock cycle at least you require data. Somehow by forwarding, if you can get the data here, that will be cool. But still it is not possible because data will be available, because through memory access you are getting the data, right? R1 gets the data after fourth clock cycle, but you require after third clock cycle, so that is impossible. That's why definitely forwarding will not work. That is what I said. Okay.